Today I'll be looking at relation, whether it's reflexive, symmetric, transitive, and if it's all three, is it an equivalence relation? Let's look at this question. So we have let x equal 1, 2, 3, 4, 5. Determine which of the following relation on x is reflexive, symmetric, transitive, an equivalence relation. If the relation is an equivalence relation, list the equivalent class. And here we have a set that says 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 3, 1, 1, 3. Now the first question you need to ask, is it reflexive? In order for it to be reflexive, we know that xx is an element of the relation. So if it is reflexive, I should have, do you remember the diagram? If you map it on the diagram, you're going to see that all the numbers map on back into itself. I have 1, 2, 3, 4, 5. So the question is, do I have 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5? The answer is yes. So therefore it is reflexive because we have all elements going back to itself. Now, the next part asks, is it symmetric? Symmetric means that if I go to one point and I come back, am I seeing those pairs in the relation? So 1, 1, if I flip it, it still remains 1, 1. 2, 2, if I flip it, it still remains 2, 2. 3, 3, if I flip it, it still remains 3, 3. 4, 4, if I flip it, it still remains 4, 4. 5, 5, if I flip it, it still remains 5, 5. 3, 1, it becomes 1, 3, and you see that we have 1, 3. So because everything that we flip, we're seeing it in the relation, then yes, it is symmetric, because when we have a pair that's in the relation and we flip that pair, we're also seeing this pair in the relation. So therefore it is symmetric. Now, transitive means if I go from point A to B, then B to C, am I seeing all of these, A, B, B, C, and AC in the set? And the answer is yes, because the pair that I can test is 3, 1. I have 3, 1 in the set, but I also have 1, 3. So both of these are in the relation. And within these two ends, I also have 3, 3 in the relation. So because 3, 1 and 1, 3 is element of the relation, and I also have 3, 3 an element of the relation, then that tells me that indeed it is transitive. Now the next question is it an equivalence relation? Yes, it is. It's an equivalence relation. Why? Because we're seeing that it is indeed transitive, it is indeed reflexive, and it's also symmetric. Determine if this is reflexive, symmetric, transitive, and equivalence relation. First things first, it says 3 divides by x plus y. So 3 divides the x and y coordinates. So we can use 1, 2, because 1, 2 is 3, and 3 divides 3. Then it also means we can have 2, 1, 1, 5, and 5, 1. 2, 4, 4, 2, 4, 5, 5, 4. So the question is it reflexive? In order for it to be reflexive, we have to have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. And you're not seeing this relation. So the answer is a no, because 1, 1, not an element of the relation. Symmetric, in this case, yes, because we can see that if I go from 1 to 2, I'll go back to 2 to 1. Then if I go 1 to 5, I'll go back to 5 to 1. So each of them, when I go to a number, I return. So yes. And you have to state why you say yes. Is it transitive? That wouldn't I know. So is it transitive? That's a no. Why? Because if I go from 1 to 2, then 2 to 1, I don't have 1, 1. Also, if I go from 2 to 4, then 4 to 2, I don't have 2, 2. So therefore, it is not an equivalence relation. Okay, determine whether the relation shown in the diagram is reflexive, symmetric, and or transitive. Reflexive, this would be no, because you can see we don't have any CC. So we need to have AA, BB, so no AA also. So we have to always state why is it not. Is it symmetric? Yes, because if I go from A to C, I go back to C, A. Then if I go from A to D, I go back to D, A, and it continues. So in this case, it's yes. Now, is it transitive? So we have to look, let's take AB. If I go from A to B, then B to A, do I have AA? The answer is no. So it is not transitive. I could take another pair. If I go from A to C, then C to A, do I have AA? The answer is no. So it's not transitive. Which of the following collections of subsets are partitions of 1, 2, 3, 4, 5, 6? If the collection is a partition, list the ordered pairs in the equivalence relation by the partition. So I have 1, 2, 2, 3, 4, 4, 5, 6. Well, this is not a partition. Partition can't have both numbers. If you realize 2 is in this partition and 2 is in this partition. 4 also is in these two partitions. So that's not a partition. It's not disjoint. It has to be fully disjoint. But this is considered to be a partition since these are disjoint sets and you see no number being repeated in the set. So it's considered to be a partition. So since these are disjoint sets, they're going to give you 1, 2, 3, 4, 5, and 6. The equivalence relation would have to write 1, 1, 2, 2, 2, 3, 2, 6. So this would be 1, 1. Then we go to 2, 2, 2, 3, then 2, 6. So 2, 3, 2, 6. Oh, I forgot to write 2, 2. Then I'm going to do it for 3. So I have 3, 2. So basically 3, 2, 3, 3, 3, 6. Then we have 6, 2, 6, 3, 6, 6. And also 5, 5. So if you look at the next one, is it a partition? Yes, because you're not seeing any odd numbers being repeated. So the set again would be, what is the equivalence relation? It would be 2, 2, 2, 4, 2, 6. Then you move on to 4. So it's going to be 4, 2, 4, 4, 4, 6. Then you move on to 6. So it's going to be 6, 2, 6, 4, 6, 6. And you're going to do the same thing for 1, 3, 1, 3, and 5. So you have 1, 1, 1, 3, 1, 5. Then you have 3, 1, 3, 3, 3, 5. Then you have 5, 1. Then we have 5, 3, and then 5, 5. For the next